This is a 1981 Gibson Explorer CMT. Normally you'd plug it into something like a Marshall JCM800 tube amplifier. But instead of paying over $1,000 for vacuum tube technology, you could instead run the guitar signal through a neural network that was trained to mimic an amplifier. Here's what that sounds like. This video is going to talk about the evolution of technology in guitar amplification. Specifically, we'll focus on how machine learning is starting to creep in and with it, potentially shift the industry. This video will also feature an interview with Laurie Huvela, who helped pioneer some of the methods behind the company that's leading the charge on this effort, Neural DSP. Tube amps are the creme de la creme of guitar amplification, despite relying on technology that came to proliferation in the World War II era and was mostly replaced by the transistor in the 1960s and 70s. When a tube amp is pushed to its extremes, it begins to squash down the tops and bottoms of the audio waveform in something that's known as clipping, or overdrive or distortion. And that can be a bad thing if you're trying to faithfully reproduce a signal as in a hi-fi system. But it turns out this can sound pretty great if used artfully, as is the case in rock and roll music. Tube amps are sought after because of the peculiar way in which they clip a signal when being driven hard. There's solid-state devices like diodes that can be used to generate a similar effect, but people generally seem to prefer the sound of tubes and use squishy words like warmer to describe them. In the 1950s and 60s, electric blues guitarists like Buddy Guy and Pat Hare would intentionally get this sound by cranking their amps as loud as they could, and push these circuit components beyond their intended operating ranges. And then later, people tried to mimic this sound by introducing audio circuitry in between the guitar and amp to make the guitar signal even louder, which would in turn push the amplifier further into distortion. And these became known as overdrive pedals, which are now so common there's even an Amazon Basics overdrive pedal. In the 90s, the Line 6 pod was introduced, which used digital signal processing, or DSP, to digitally model amplifiers and effects. Most commercial systems treat the signal chain as a series of blocks, which represent filters and nonlinear distortion units. And then the idea is that the blocks have parameters which you set to try to match the audio processing characteristics of the matching subcircuit in the real amplifier. So the process of building your model is to introduce signals into the real amplifier and measure their circuit responses, and then adapt the parameters in your model so that the behavior matches as close as possible to the real thing. Perhaps the most popular modeling amplifier right now is the Kemper Profiler. And the most famous feature about the Kemper Profiler is that it can create your own digital clones of your equipment. So you plug the Kemper's output into the input of your gear, and then you put a microphone in front. And then the Kemper sends a signal that it knows to the gear, it listens to the output, and then internally it figures out how to directly map input to output to essentially replace your gear with a digital model. And the great thing about this, aside from it sounds pretty much imperceptibly different from the original, is that you can upload it to the internet and share it. And it's a lot easier to get a profile than it is to track down a tube amp from the 1960s and pay thousands of dollars. There are thousands of such profiles available, and entire businesses built on providing high-quality replicas of this vintage, highly sought-after gear. Here, for example, is a profile of a Soldano amp. So far, none of this has relied on modern machine learning, but that is starting to change. There's a newly emerging company that's making a pretty big splash called Neural DSP. They've released a number of software plugins that are amp models and effects models that sound amazing and rely on machine learning under the hood. So here, for example, is the Nolly archetype from Neural DSP. Similar to the Kemper Profiler, the new Quad Cortex from Neural DSP has rig cloning capabilities. And they use incoming guitar signal and the sound of the rig that you want to clone as training data for a neural network, which is trained on the actual device. Neural DSP hasn't discussed the details of their technology publicly, but there's some papers on using deep learning for guitar-related use cases from some researchers that work there that give us some high-level clues. So they're likely using a black box modeling approach, which means they're fitting a machine learning model that directly maps the input guitar sound to the output sound that you expect from the rig that you're trying to clone. And this is different from, say, a white box modeling approach, which requires you to have some understanding of the underlying circuit of the amp so that you can separately model different components of that circuit. In this paper, one of the common architectures they look at is WaveNet, which comes from the DeepMind group and was used in speech synthesis applications that might be applicable to things like Siri and Alexa. But what's different here is that we're dealing with high quality audio, which means 48,000 samples per second. And that's just a ton of data. A traditional language modeling task wouldn't have anything close to 48,000 samples for generating a prediction. Another challenge here is that audio circuits respond differently to different frequencies, which is why there's a guitar amplifier as a distinct thing from a bass guitar amplifier. And to describe the highest frequency components, you need all 48,000 samples per second. But the lowest frequency components only cycle at around 20 times per second. So all of those samples are essentially noise in describing what's happening at that time scale. So the complicated part is that we're having to simultaneously process and model frequencies that span several orders of magnitude. A key innovation in the WaveNet architecture is this notion of summarizing the audio hierarchically. So the deeper you go, the further back you can see, the less fine structure and the more high level of a summary you have of the audio. These are called dilated convolutions, and they're implemented by having each layer ignore 2 times as many inputs as the previous layer, as in this diagram. The result is that your receptive field increases exponentially with the number of layers. But this all sounds complicated. Why throw machine learning at this task when Kemper has obviously shown that they can do a great job of creating high quality replicas of a rig? Well, the primary limitation of these traditional black box techniques from DSP is that they can't elegantly model the knobs on the amp that you can twist. So effectively, if you want to start twisting the knobs, you need to build a different model for each configuration. But the number of possible configurations scales exponentially with the number of knobs, which is usually around 5 or more. And it just becomes totally impractical to build a different model for every combination of values for each knob. So what effectively happens is that they capture a single setting and then they apply generic DSP post-processing effects to simulate what the knobs would do. But at that point, you're no longer capturing the response of the real amplifier of what it would be like to actually twist that knob. You're just throwing generic processing on top of a single setting. But with machine learning, we can use the knob values as just another input to the model and learn the interactions and how they impact the sound. This assumes, of course, we have all the training data that captures all these interactions, and that's no trivial task. But in this paper, by some of the same researchers at Neural DSP, they use a SPICE simulator, which is slow and not suitable for real-time use, but it is accurate. And they can digitally twist the knobs on the SPICE simulator to generate the training data to fit their model. And they compare this to the traditional block-oriented DSP techniques and show that it works quite well and actually outperforms those traditional techniques. I got a chance to sit down with Lauri Huvela from Neural DSP and pick his brain a little bit. He shared a lot of awesome insight about this intersection between guitar circuit modeling and machine learning. So that'll play in just a second, but before we get there, let me mention, if you would like to play with this stuff and either train some neural networks on gear or play through some pre-trained ones, there's an open source project called GuitarML. And they have the code to help you do the training. They also have a VST plugin wrapper so that these models can be deployed and you can play through them in real time with your guitar and your computer and plug it into like a digital audio workstation. So super cool stuff. You should check it out. And now onto the interview. So Lauri, thanks for joining today. Really looking forward to this conversation. This is going to be about the company you're from, Neural DSP, and some of the cool stuff about the intersection of machine learning and guitar, which I think is interest of both of us and hopefully to the broader community. So this is a really cool application area, and thanks again for being here. Really looking forward to it. Can you tell us just a little bit about Neural DSP, what the company does and specializes in?
Yeah, we're a startup from Helsinki. We're doing basically guitar sounds with a lot of machine learning involved. Two main product lines are plugins, GuitarAML models. The latest one is a archetype Gojira with a Duplantier, and it's kind of metal focused, but moving more to like a general guitar sounds. And there's also our hardware product, Quad Cortex, launching really soon, or we're shipping them to the pre-orders starting, I think, next week.
That's really exciting. Yeah. I saw the Gojira video yesterday and was blown away. That was just so cool. What a great band to have on the roster. You know, that's
they're one of my favorites. Yeah.
So are you a guitar player then?
Yeah, well, most of us are some sort of musicians. Like guitar playing is the focus. Yeah, but it's almost like most of the, like, especially the machine learning team is kind of just people who did a PhD in something, and then just because they're passionate about music, kind of somehow the stars aligned, and we just it's like for me myself, it's kind of a side project, went crazy, and ended up from like speech synthesis to doing audio.
It's like the dream, though. You know, it's like if you play guitar and you're into machine learning, it's like, what cooler company or project to work on than that, you know?
Yeah, I agree.
So can you talk a little bit about your background? You mentioned speech synthesis there. Was that like your PhD focus? Or?
Yeah. I just defended this summer, and I was basically doing like it's also like my background is like original background is kind of in digital signal processing. Then I started doing speech synthesis, and then during my PhD, everything just morphed into this like a fully neural synthesis, like wavenets and RNNs for waveform generation. That's like basically the classic audio processing side of speech was enveloped in this neural net world, and it's a lot of, like a lot of tech transfer from that domain. It's seemed like even like a low hanging fruit as the original paper that got me into this is like a side project where we just used a modified WaveNet type architecture for modeling guitar amps. We started with something simple like a tube screamer, and that worked super well. And like, let's go a bit higher. And the first paper was like I think a Fender Bassman preamp that we modeled, and that works super well. Yeah, and that's things started escalating from that. But it's like, yeah, it's the first these models kind of broke through in speech synthesis. So that's my background really.
Well, that makes a nice segue into what is it that makes modeling guitar amps hard? Like, why can't you just, for example, figure out how each frequency is impacted by the circuit and just sort of like go through that component wise and then sum them all together in the end?
Yeah, well, like a very simple model. If you just look at the frequency response, that essentially are building a linear model, and guitar amps are highly nonlinear. It depends on how hard you put stuff in. There's going to be distortion. There's going to be like intermodulation distortion. It's the response changes dynamically. It's not just the frequency response that you have to match in a guitar amp, but yeah, there's all the kind of distortion characteristic and like compression going on, and it's a very dynamic system. And your typical model would be like first frequency matching idea would be you just do a linear time invariant model, and that's not going to cut it at all. So you would need to go to, let's say, frequency response that is time varying, but that's already gets really convoluted. You would need to change that rapidly, and you still don't get the distortion characteristics right easily. But just yeah, they're very complex systems, or the behavior is complex. Just like looking at guitar amp schematics, it's not that that doesn't look too hard.
Right.
But the tubes are hard. Just modeling how vacuum tubes work, that's hasn't been like nailed perfectly.
Because they also have interactions with like the transformer and like sag and all these concepts of these nonlinear couplings between other circuit elements that I'm sure that it's just got to be incredibly difficult.
Yeah, and typically you would even have some kind of feedback connections from the power amp back to that deeper in the amp, and it's all of if you just do circuit analysis for this, like and some people do, and it's like there's a lot of great virtual analog models which are like very detailed circuit analysis, and you go basically like solving these partial differential equations real time, and that gets really hairy really soon. So you got to cut corners and or know where to cut the corners. That's an art form to itself. But another kind of nasty property there is you typically would need to use iterative solvers, and then you get this kind of not deterministic runtime, and that's a whole another topic. I'm not really an expert in that. That's not really the way I want to do guitar amp modeling either.
Right. Yeah, there seems like machine learning offers some unique advantages to kind of get around some of those things. But before we get there, can you give us an outline of I don't know, the basics of like how Line 6, Axe effects, Kemper, these more traditional approaches that aren't using machine learning? Can you just give us a one paragraph or so explanation at a high level of how they go about solving some of these problems and doing the modeling?
Well, this is just the guesstimates, because they're not really like disclosing what they do in detail. like the kind of classical DSP approach for doing this is basically you look at the schematic, try to identify some functional blocks in there, and say, this is I can approximate this with a filter and a wave shaper, another filter and another wave shaper, and then you go into like do some calculations and try to approximate the frequency response of a block or how it would distort, and start chaining these filter wave shapers and basically tune it by hand and go in and measure the amp and play some sweeps through it, and just kind of manually transfer data from a physical device to this kind of block-oriented DSP.
Oh, so you're saying they'll take like a functional block in the circuit, and they'll have this linear and nonlinear blocks with parameters, and then they'll try to fit the output of that to the output of that part of the circuit? Because I assume they just sort of had like input and output of the amp, but not necessarily the intermediate voltages within the circuit.
Yeah, if you want to have a good model with this approach, I think you'll need to go to kind of also probing intermediate.
Oh, interesting.
Intermediate responses. It's like if you just do a kind of end-to-end block oriented, it's really hard to tune. It's that's what deep learning does great is that you can actually like there is an analogy to it. Like you typically have like a weight matrix or a linear part and then some activation function, and you kind of keep on stacking those. But I think neural net or deep learning is really the only good way of that we currently know of that we can actually end-to-end estimate these parameters. It's like so the classical approach, I think, there's a lot of this kind of intermediate state probing to tune the whole system.
Do they do it sort of one block at a time, or as you said, deep learning does it kind of end to end, and each block is kind of being jointly optimized? But I imagine that they don't have that luxury. Is that right?
No. Yeah. If you do the classic DSP where you basically have to, or at least like it helps you because you can actually like break apart the amp. It's a lot of work, but you can do circuit analysis and use modeling software like Spice or like circuit emulation software, and actually do the measurements in software to some extent. For like there are some segments that are like passive parts of an amp, so those are like well understood how you would go about modeling those. So those parts, it's like very easy to, let's say you have the tone stack part of an amp, and that's basically linear. You can just do circuit analysis and a kind of model pops out from that. That's kind of standard electrical engineering. But like some other parts, if you have like the gain stages, you have a lot of tubes in series, and
right.
It's a bit hard to model, but yeah, the kind of classical approach to this, I think, is that you need to go probing in or do some circuit analysis or a combination of the two. So yeah, it's really like not that many people who can do it. It's very like labor intensive and expert labor intensive.
Wow.
Another approach which looks a bit more like the neural net approach is this the classical black box modeling approaches, which I can't really go into detail on those, but at least on the academic space, there's like the Felix Ikas and Udo Zolzer paper where they basically constrained to this kind of two-part model, which is like a filter wave shaper filter, and then they make some clever assumptions about what kind of signals you have to pass through to be able to estimate the parameters for that. But it's like a very, very rigid topology, or it's like a simple fixed architecture that you can estimate with that. And if you want to grow the system somehow, you can just estimate the parameters.
So one thing about using these models as an amplifier is you need to have really low latency. I assume it has to be under 10 milliseconds. Maybe you can tell us numbers, what you think is acceptable for real time. But anything more than that, it starts being a distraction to the guitar player.
Yeah,
right? They can kind of feel it. But
yeah, and that's like my rule of thumb for algorithm design would be that there should be no algorithmic latency, because there's already like the round trip latency like adds up just from like the audio converters and all that. So like because there are alternatives, like just if you have a causal wavenet type or like any type of causal convolution net, that's zero algorithmic latency. Or another alternative is these RNN type models, which Alec Wright has been from Aalto University. They're kind of connected. We've been involved in that as well before moving to Neural. But yeah, it's yeah, it's like from a modeler's perspective, just make your models causal and you're good. There's like zero algorithmic latency.
So can you define those terms?
Yeah, so, causal is like you can't use information from the future, or if you want to use information from the future in your model, you basically need to wait for the future to happen, and that introduces some latency. So if I input the signal at this very instant, yeah, that's the information that's available.
Right.
Typically, there's a buffer size to a digital audio processing, but still, that's for example, you get like a buffer of 32 samples, but you need to process that in one go. So you can't wait for any information from the next buffer. So if your algorithm requires information from the next buffer to function properly, you would need to wait for that buffer to come in, and that's your like total latency for the thing becomes 64 samples.
So that's what you mean by zero algorithmic latency, that there's also no future dependence.
Yeah, that's the like the algorithm side of like the causality is. It's like don't make the algorithm depend on the future, at least not by much, because that's 10 milliseconds is a good rule of thumb. That's basically what it's like if your amp is standing at a few meters away, you get just the sound propagation through air is something like 10
Oh, yeah, I hadn't thought of it that way. That's interesting.
Yeah, but that's a good yardstick for calibration. If someone says that they can feel like two milliseconds of latency or 3 milliseconds, maybe in certain conditions, but if you're like playing in a room, that kind of gets smoothed away. But yeah, but it's like the smaller the better. 10 milliseconds is probably, I think, a good rule of thumb. I try to go lower in my DAW if I can, but yeah.
Well, the other side of the coin is you're trying to process high quality audio, like 48,000 samples per second or something like that, 44 maybe.
Yeah, 44 is the kind of CD quality, or 48. That's a lot of samples. Like all the speech synthesizer, like the initial wavenet was super slow, and it worked on like 16 kilohertz sample rate, which is less than half of what like an acceptable guitar application would do. So yeah, there's a kind of the implementation in something else than Python. Like GPUs are out of the question for real-time inference. Like it's just a kind of round trip for just transferring the data to a GPU and back to your sound card. It's that already kind of caps the inference rate.
Oh,
something
really?
that's like far from real time. So rather that's just like the current hardware. So it's probably if you integrate that on everything on a system on a chip and have a parallel processing unit, which is like could spend some time with a new M1 chip on my MacBook, but I think that's a really nice direction to go, to just like have this parallel computation capability that can also tie in with low latency. But like just with the current pipelines with the GPUs and how all of that works, that's really not great for real time. And also it's like the GPUs are also great if you're like training in a batch mode where you've kind of already observed all your signals or your inputs, so you've kind of waited for the future to happen already, so you can kind of just process everything on a one go, and GPUs are great for that. But for real time, probably better off. You're basically doing sequential processing, so CPUs are great for that. A low level, well, C++ is that low level, not necessarily, but just going for like optimized implementations there, it's super important.
Well, one thing
also scaling down the model size is another challenge, because the original wavenets are so kind of huge.
Yeah, the thing I don't quite understand how it could work is that the frequencies that we care about span several orders of magnitude, right? So like for the highest frequency, around 20 kilohertz, you obviously don't need much of a buffer size to capture the information in those frequencies.
Yep.
But for something like the lowest bands around 20 hertz, you might need 10 milliseconds of audio just to capture the waveform of a full cycle. And maybe that's not important, but it seems like just to kind of maintain the information in something like a WaveNet architecture, you would need, I don't know, something like double-digit milliseconds of audio to be passed in for inference. Is that not correct, or how is that handled? I understand if you have a recurrent net, then the memory state could kind of keep track of that stuff, but I'm not sure how it would work with a WaveNet.
Well, WaveNets also kind of stateful. You basically have these like dilation buffers that so you don't need to kind of recompute the whole receptive field. But it's still the kind of effective receptive field for a WaveNet. You can quite easily make it long. It's to the order of milliseconds still.
So is the challenge then to kind of implement the sampling piece of like you're keeping all this state and memory from previous inference request, and now you have to kind of look up these different dilation factors? Is that difficult?
Well, it's a bit tricky, but there's like being public implement or even public implementations of it. It's basically you can like take advantage of the fact that there's holes in the convolutions, so you don't need to compute everything at every sample, but you can kind of just store the values from a previous one, and just there's basically like a multiple clock rates at the different dilation factors going in the network. So yeah, it's a complicated model, and it's really hard to optimize for real time, because it's just it's very granular. You can't do this kind of RNNs are great because you can just do large matrix multiplications for everything, and it's like optimizing compilers can squeeze a lot out of those. So it's like the iteration in the speech side it's like first you had the WaveNet, and then about a year later Google guys published this efficient neural synthesis paper where they had this RNN based model, and it's like the industry applications have been a lot of them on the speech side that's used to like being RNN based, just because it's so much easier to optimize for real time. WaveNets are complicated. That's the way to put it. Yeah.
So transformers are kind of taking over the world. Do you see them making an impact here, or is there kind of fundamental constraints around these sorts of things we're talking about with size and inference time that won't make that work well?
Well, it's also not that complicated in audio, and transformers are so you're basically trying to like fill in the gaps, but with a transformer. But here you're always kind of it's for audio processing. This is actually a nicely simple regression problems. It's to me it's almost like prototypical black box, just like signal to signal. It's like you have no issues with alignment, or at least it's fairly easy to solve these alignment issues. It's like even transformers are powerful, but the for this it could be just like overly complicated. It's
So do you think it's the case that parallel is a good target because then we can kind of have larger models and distribute the computation, or you seem to say that kind of the target is sequential?
Yeah, so that's like the inference latency is like the latency constraint here is really unique because you really need to push it down. So that's a bit of a constraint. And like, of course, if you can do real-time parallel inference, then you can make your models wider, not necessarily deeper. Well, depends what you do, but yeah, the latency is something that you always have to keep in mind when you're working with audio or this kind of real-time audio processing. Of course, if you can go into like offline batch mode processing, there's like lots of other applications where you can do that, and it's like transformer-based acoustic models are like becoming the state of art in the text-to-speech scene. But those are typically not designed for real time. It's like you have this kind of acceptable latencies is some tens of milliseconds, but it's it's a bit of a different like application constraint.
Yeah, so you mentioned GPU doesn't work well because basically the data transfer rate is already hitting up against the latencies you require.
Yeah.
So CPU, maybe conceivably you could do something in parallel there. I don't know what kind of overhead that adds. I'm not in this real-time world. But when you look at the hardware specs of the quad cortex that Neural DSP is releasing soon, it talks about these Shark DSP chips, which I don't know anything about this hardware world, but if you're able to say, does the inference of these models happen on those DSP chips, or is there some kind of other dedicated CPU where the model inference happens?
Yeah, it's using the Shark cores there's a lot of nice neural net models running on the Cortex.
So does that add like a new challenge for you in terms of translating the models into something that can execute on Sharks? I don't know what the
it's a bit of a software engineering problem to kind of that's like basically we just have to implement our own inference libraries and exporters from let's say if you train a model in PyTorch and you want to export that into like an embedded C-based environment, you just have to build a lot of the pipeline yourself. But it's in the end, it's like the inference code running there is like C-based. Just it looks a lot like just a lot like optimized DSP code.
Have you gotten your hands dirty with that side of it, or are you mainly just the model builder?
Well, yeah, I think I built a lot of the exporting pipelines, and I'm looking at the code on the C side as well. So it's I didn't write that a lot of it I didn't write, but yeah, it's at least I'm kind of involved in the kind of vertical integration of going from kind of machine learning familiar Python world to the C side. It's like, or it's I think it's even more exciting for the capture feature that there we're actually training models. So that seemed a bit like a crazy idea to do backprop on a user device embedded system.
I hadn't thought of that. Yeah, that is.
Yeah, so that's like AutoGrad, it's out. You have to like implement your own backpropagation for your model and all that. So that's
Yeah. So for anyone that is listening that doesn't know what he's talking about, one of the features of the Quad Cortex is that you have your own equipment, and you can basically train a neural network to copy your equipment so that you can, kind of toss the hardware out or sell it or whatever, but then you still have this digital clone of it. And that's similar kind of in concept to at least what the Kemper profiler does, but in this case is using neural nets. So you're saying that you've had to implement those training libraries on this so that it will happen on this embedded DSP chip, which is must have been a ton of work to recreate all.
Yeah, it's a ton of work, and also it's just like checking that it's all correct, and just like a lot of double checking against PyTorch and figuring out like, well, how does backprop for convolution actually work?
Oh yeah, I recently made a blog post that implemented graph convolutional networks using NumPy, and I had to do the same thing. And like, you look at the equations, you read the papers, and it just sort of becomes ingrained in your memory. But then when it comes time to actually do it from scratch with the matrices and getting the orders of them, and then you start thinking about dimensionality and like, oh wait, do I sum over the batch here, or do I keep passing it through? Like, it gets really complicated, and
it does.
I can't imagine doing it on a real life product that I'm going to ship out the door. So kudos to you guys.
It was crazy, but I'm super happy with how it turned out. It's just the correctness is one thing, but efficiency is another, and that's something we spent a lot of time just make it efficient computationally, and also make it converge fast enough that you can, like, you don't have to wait for. It's currently taking like 4 minutes or 3 minutes, but end to end with like recording and training that.
And how much audio do you need for that?
It's not recording that much. It's like a half a minute or so.
Oh wow.
Yeah, because it's like a snapshot of the amp. So it's like if you want to do, it's just like one setting of controls. So that's if you want to start turning the knobs or do conditional models, that's a whole another level of complexity, and just the data collection of that it's like you wouldn't want to have your user turn the knobs. Like that's like, I don't think we could make that robust enough. Like, now turn the volume knob to 1. Now turn it to 2. Repeat the same for like all the tone knobs, and that's just too much.
That dovetails very well with my next question, which was about these traditional methods can't model the knobs well, or at least in an elegant way. You can maybe capture different models for each configuration of knobs that you think are important or something like that, as I understand it. But then you have like this exponential increase in the number of models you need to keep. And I'm sure the people that use these techniques have come up with clever ways of reducing that complexity. But one of the cool things about machine learning is that you can include the knobs as just another input to the model and sort of condition the model parameters on that. And as you mentioned, the data collection piece is really difficult there. And I noticed in one of your papers, I think you referenced it earlier, of this Fender-Baseman model.
Right.
You used a SPICE, some software circuit analysis or simulation software to generate the training data. Does that work well? Is that kind of a good strategy of how you would generate? Because there's these obvious benefits of that you can kind of digitally control the knobs, and then they're faithful and reproducible and all that, as opposed to kind of trying to manually set them. Is that the path really forward?
Well, it's works really well if your SPICE model is accurate. So if there's tubes in the circuit, that becomes questionable, because the digital models, even with these like partial or differential equation solving tools, the tube models in those are like still I don't think they're up to the task for amp modeling, but you can do stuff like mostly linear circuits like WAS or like modulated filter type stuff. That so some of those are actually on QC as well. It's like the WAS WA models are neural nets, because the Spice is a great way for collecting data for those.
So, do you think there's opportunity for machine learning to kind of disrupt that space of where, you know, maybe you have a 12AX7 tube and you build a neural net to map input to output and characterize that as a function that, you know, maybe it's conditioned on material properties as well or something like that, so that you don't have to do it in real time, but you might have a better way of generating data in something like Spice, which could then feed back to help you build the models that we're talking about in this other context that are real time.
That's a good idea. I've tried it, but yeah, that's just like replacing the Spice internals with some kind of neural net models. I think well worth trying. I haven't tried that.
Last question is, if you if someone out there wanted to play with, for instance, modeling the Baseman, I think you had a paper out maybe during your academic career that was about that and had generated data from the Spice model. Is that data publicly available for people to play with, do you know? Or
Spice data, I don't think we open sourced it. I don't see why not. But yeah, that would be nice to have some kind of like conditional modeling benchmark for people to play around with. Like the stuff that's currently online, it's mostly these like snapshot style models. So it's like what's stopping us from doing, or the online community from doing conditional models or research on those, it's really the data availability. Of course, you can go about, if you just do one control, do 10 recordings or 11, so like go from 0 to 10 on your amp, or like 2 controls is still feasible, but and you still get like reasonable models like should learn to interpolate. But the original data set, I don't think we open sourced it. Might be somewhere still on the university servers, but it's.
So were you guys involved at all in, you know, there's this open source project. I've actually seen a few different forks of it or something, but the larger project is GuitarML, but it has these smart, I forget exactly what it is called, but they essentially have a couple pedals and an amp, and they're using wave nets, and it seems closely aligned, at least with the techniques that I saw from the papers I read from your group. I didn't know if you guys were involved, or if there was like a sister research group, or if it was just they came across your papers.
I think it's using, they're using the like we did open source the WaveNet inference code back in the day, and that's on GitHub, and they're I think directly using that in the WaveNet flavor of that project. I think I also gave a few small tips on how to because they popped up this like basically a PyTorch implementation of the training code, which we for some we were kind of already talking with guys at Neural and back in the Alto days, and like decided not to share the like the training scripts that we had. Like somebody did a PyTorch implementation that seemed mostly correct or like compatible with what we were doing on the open source inference code. So there's his name Keith Bloimer, who's like started the GuitarML project. I think I gave him just a few debugging pointers of how to kind of tie these like the open source resources together. But yeah, I've been following the projects. Not really like actively contributing, but.
So one kind of question I had on that integration piece, because it uses the Juice framework to wrap it into a plugin, and and that's C++. But then things like PyTorch will allow you to basically export your models in C++ and just use those directly as opposed to writing your own inference code. Do you find that you have to write your own inference code because there's optimizations necessary there for getting the real-time performance, or were those tools just not available at the time?
Yeah, it's a bit of a combination of both. Like our original code that we had was in TensorFlow, and that like there definitely wasn't a real-time capable C++ code at that time. Also, the WaveNet model itself has these intricacies that are, I don't think you can get those out of the box, even though for that's PyTorch C++. We probably could get an RNN running real time with just PyTorch's, or at least like some configuration of an RNN running with PyTorch's C++ API. But there's it's like it's still it's a bit of a like a trade-off between optimization and hard coding things versus like generality, and these toolkits are leaning on the generality side because they're like mostly for research, or at least they kind of arose from the research side of things. So there's still like holding on to this baggage of generality, like
right.
There some trade-offs you need to make.
Is my understanding correct in general about the difficulty of modeling these circuits, that essentially the more distortion, the harder it is? Like the more nonlinearities, the more harmonics. And if that's correct, I've noticed a lot of the focus of Neural DSP has been kind of on the heavy metal side, at least in the ones I've come across. Maybe there's some selection bias there, but like Gojira and Nolly and stuff, it's very high gain. It seems like the hardest problem to tackle. Is that correct? And if so, is it just like that you've basically solved it and have the confidence, or is it like we're going to start here and then the rest will be easy after that? Or
yeah, I think there's like two effects that are kind of independent. Somehow the kind of heavy tones, the buying public for those is very tech curious, so they're kind of they take they don't necessarily want the physical thing, or they're not that like nostalgic about the. So it's I think it's a very fruitful scene to start with these plugins. It's like the tech curious tech metal scene. So it's partially business thing, and also it's like just the background of the people in the company are like well connected. Like especially the CEO, Doug Castro, is run Dark Glass for a long time. It's like it's basically he's very, very well connected in the kind of heavier music industry. So that's not really a like a algorithm question per se. Modeling heavy tones or cleaner tones. Right. I guess that if you go and read the forums, like what the people say is that the hardest to model is the edge-of-breakup tones. So it's the kind of in between. So just like when you roll off your tone pot on your guitar and you want to get the like right response of like if you dig in, you want to get some distortion. If you play lightly, you want it to be clean. So that's the.
Yeah, I found when listening to some of the sound samples of the projects linked to in the references of your papers, that like the big muff or the really heavy fuzz settings.
Yeah, that's hard.
Yeah, that seemed like the hard part because there were all these weird frequencies that popped up that it's just got to be super tough to model.
Yeah, those are, yeah, it's like this extreme saturation is hard to model, especially with gradient descent. It's hard to model because it's like you basically want to hard clip, or even go to like a pure sine function, or not like a sinusoidal sine function, but a like a plus or minus one sine function.
Oh,
so like
yeah.
basically hard clip. How do you backprop through that? Like you go to an extreme saturation, you basically clip everything. The gradient of that is 0. How do you backprop? That's hard, and that's part of the. You're basically operating largely on a saturation region for your like neural net nonlinearities, and you somehow have to deal with that when you're going to extreme high gain.
Very interesting.
Of course, it's again on the cleanup side of things, it's then hard to like, where do you put the filtering? It's like if you have some type of like overspecified model, there's multiple solutions that are appropriate. Like it's basically like if you have multiple filters that are not distorting that much, how do you distribute the filtering? It's clearly like a non-unique solution.
So any last things you want to plug or talk about? Any websites or Twitter handles or anything like that?
For Neural DSP research, yeah, I don't know.
Or just for you personally?
For me personally, I don't really do Twitter.
Smart move.
Yeah, check my GitHub.
Great. Well, stick around for a second. I'll wrap up the recording, but thanks again. This has been really interesting and informative. I hope everyone else gets as much out of it as I did, so I appreciate it.
Yeah, thanks for having me.